module 3, which is in continuation. This presentation is in continuation with the RE model, the analysis, RE model analysis of BJT amplifier. This is the second method for doing the modeling of a amplifier. So the advantages of RE model is that the parameters are defined by the actual operating conditions. The parameters of the hybrid equivalent circuits are defined in general terms for any operating condition. So complete hybrid equivalent circuit. Here in this fashion you will be situating or drawing a model of a transistor for any biasing circuit, whether it's a common emitter, self bias, or a common emitter voltage divider. So hybrid equivalent circuit HI, HRV0, HF, II, H0. So here everything is stated. H11 input resistance is HI. H12 reverse transfer voltage gain HR. H21 forward transfer current ratio HF. H22 output conductance, which is equal to H0. So common emitter hybrid equivalent circuit. In an ideal case, This is an equivalent circuit that is drawn for common emitter configuration. So here you can see the equivalent circuit which was shown independently before this particular presentation of a slide. Here you can see HIE, a voltage source HRE, VCE, then a current source at the output which is HFE, IB and HOE. So the net current will be the sum of the base current plus sum of the collector current, which is HFE, IB. So one question can appear over here. Draw an equivalent circuit of an ideal common emitter transistor configuration. The answer to that is this. Take a simple example. Here emitter current is given, which is 2.5 milliamperes. HFE is 140. HOE is 25 microsiemens or micro or more. HOB is 0.5 microsiemens. So determine the common emitter hybrid equivalent circuit. So RE is 26 millivolts upon I. This we have already seen when we were dealing with RE model. So HIE is equal to beta times RE. This is a very important relation. Input impedance HIE is equal to beta RE. Output impedance R0, that is equal to 1 upon HOE. So it should be equal to 50 ohms. So this particular model shows the relation of hybrid pi model with the RE model. So things to remember over here, RE is directly related to HIE through a beta parameter, and 1 upon HOE, which is the output admittance, it is equal to the resistance R0, which is used in RE model. Fixed biasing configuration. So here you can see this resistance, this terminal should be grounded. So here we are drawing first the hybrid pi model of this transistor configuration, which is in common emitter. So HIE is the input resistance, HFE IB is the output current flowing into the emitter terminal, and 1 upon HOE is the resistance offered by the transistor along with the load which is connected to the system, that is transistor device system. RC, RB is the input impedance that is connected between the base and VCC, which is grounded in case of AC analysis. So your input resistance ZI is RB parallel HIE. Z0 is impedance by looking back into the network. So current source will act as an open circuit, and certainly your resistance output impedance is a parallel combination of 1 upon HOE parallel RC, which is shown in this equation 2. Then we are in a position to find out the voltage gain and the current gain. So Ri dash is a parallel combination of 1 upon HOE parallel RC at the output terminal. So your output voltage is equal to I0. Of course, it's a negative sign, the current flowing out of the output terminal. So V0 is equal to minus I0 R dash. I0 is substantially equal to the collector current. So it is equal to minus IC RC dash. Substitute the value of IC equal to HFE IB. So IB we can find out from the input side. So here this is VIE is the voltage present between the base and the emitter terminal. So IB is equal to VI upon HIE. So substitute the value of IB in the voltage relation, which is equal to V0 is equal to minus HFE VI upon HIE R dash. So AV is equal to V0 upon VI. Take the ratio of voltage gain from this relation V0 upon VI, which will give you minus HIE into RC parallel 1 upon HOE upon HFE. So this defines my voltage gain given by an equation 3. To find out the current gain, we assume RB to be parallel than HIE. 1 upon HOE is greater than or equal to 10 times RC. We find IB is equal to base current is equal to input current and output current is equal to the collector current. So you write the relation that HFE IB is equal to HFE II. This has come from very simple relation, that is IC is equal to HFE IB. Since here we can see I0 is equal to IC and IB is equal to II, I can very conveniently replace these current components IB and IC by II and I0. So therefore I0 is equal to HFE II. So take the ratio of the current gain I0 upon II is equal to HFE, which is given in equation 4. So voltage divider bias, hybrid equivalent circuit of this. First understand the biasing circuit. This is a common emitter configuration. Here you can see the capacitors C1 and C2, which are the bypass capacitor. And CE is a coupling capacitor. Sorry, here C1 and C2 are the coupling capacitors and CE is the bypass capacitor. So when at high frequencies, these capacitors are going to be short circuited, allowing the input current to provide an active source to the transistor and allowing the response to be obtained from the network through C2. CE is a bypass capacitor. So this also shorts at higher frequency and this resistance will be shorted because of the effect of CE at higher frequency. So we'll redraw the circuit based on this. This is a circuit which is actively drawn for common emitter configuration in ideal state when no external components are connected. So the similar way you draw, this is HIE, HFE, IB, 1 upon HOE. These components are very common. In case of RE parameter, RE model, it will be slightly different, which I can show here by drawing it. ideal parameter only for transistor I am drawing. So this is Re. This is current source, which we talk as beta times IB, and then a resistance R0 over here. So you can see the similarity. This is an RE model. This is a RE model, and this is your hybrid pi equivalent model. So HIE can be replaced by RE, and R0 is replaced by 1 upon HOE. Current source remains the same, where beta is equal to HFE. So input impedance from figure 1, by using the DC analysis, we can find out RB is equal to R dash, where R dash can be written as R dash is a combination of R1 parallel R2 which is also equal to the base resistance RB. Fine. So Zi is equal to RB dash is equal to Ri dash. From figure 2 over here, Z0 is directly equal to RC. Here this is considered because 1 upon, even if we take a parallel combination of 1 upon HOE parallel RC, 1 upon HOE is going to be a very small value, and which is an ignorant value. So it is directly equal to RC. In order to find out the voltage gain and the current gain, here what we are doing is that we are taking the current flow through this parallel combination 1 upon HOE and RC times I0, and voltage at the input terminal is IB times HIE. So how is I0 related to IB? I0 is equal to IC, and IC is definitely equal to HFE times IB. So when you substitute the values of IC and IB in the numerator and denominator, you will get this relation HFE in bracket RC parallel 1 upon HOE upon HIE. So let me try to explain you. So V0 is equal to minus I0 into parallel combination of RC and 1 upon HOE. Similarly, here input voltage VI this is equal to IB into HIE. The relation between I0 and IB is I0 is equal to IC, which is equal to HFE IB. So this will give you a voltage gain. Take a ratio of V0 upon Vi. So this is equal to, substitute the values over here, minus HFE IB into RC parallel 1 upon HOE upon IB HIE. So this IB and this IB are same, so they'll cancel out, which gives you this relation. So minus HFE RC parallel 1 upon HOE upon HIE. Similarly, when you take the ratio of the currents, you should be able to find out the overall current gain. So overall current gain AI this is equal to I0 upon II. So that is why here R1 parallel R2 is coming, which is in series with HIE, right? And HFE parallel R1 upon R2. So this gives your relation, equation 4. Unbypassed emitter. So in this case, first you have to draw the hybrid equivalent circuit. This particular circuit, what is drawn, is for a common emitter configuration, which is given over here for an ideal situation, this transistor. So HI and HFE are given. Based on that, this particular circuit is drawn. Emitter resistance is present. So we have shown in the circuit bypass capacitor. Here, this is a coupling capacitor. These two, C1 and C2 are the coupling capacitors. Ci or C0 so called sometimes. So Ci and C0 are the coupling capacitors. At high frequency, they short out. So here it is shorted. And resistance RB is present between the base and the emitter. RC is present between the collector and the emitter terminal. So we have to find out the impedances Zi and Z0. First we'll try to find out what is an input impedance ZB over here. So ZB is ZB is a sum of HFE and RE. This RE and RE is same. RE is same as small re. Okay. Therefore, Zi is equal to RB, capital RB parallel ZB. In AC equivalent circuit, capital RB is again same as small, which is written in the suffix, capital R to the suffix B. Okay. So hybrid equivalent circuit with an unbypassed emitter resistor. So if this resistor is, This is called as an unbypassed emitter resistor. So Z0 is equal to RC. It is very obvious and can be seen from here. Find out the voltage gain, find out the current I0, find out the output voltage V0, which is equal to I0 in minus I0 into RC. Now I0 minus I0 is equal to HFE IB. So output voltage V0 is equal to HFE IB into RC. Similarly, find out the input voltage VI over here, which is nothing but IB 1 plus beta times IB into HIE plus RE. So HIE being very small, it is ignored. So it's a ratio of HFE RC upon HFE RE. So your output voltage V0 is equal to minus I0 RC I0 is equal to IC is equal to HFE IB So substitute the value over here, which will give you V0 is equal to minus HFE IB So when you are finding out the input voltage VI, this is equal to IB HFE plus 1 plus beta times RE Alright. So in this case, of course here one parameter is missing, that is here it should be IB. What is happening is that this IB HFE and IB HRE, this is going to be very small. So your input voltage VI is equal to HFE RE So that is why your voltage gain, when it is taken as a ratio of V0 upon VI, this will turn out to be minus RC upon RE. Alright, so it is shown over here. This. So in this way you can derive the voltage gain.